So, at the beginning of this module, I talked a little bit about the history of computation for the first two lectures. By the end of the two lectures, I started talking about the end of the 19th century and the beginning of the 20th century. And I told you about Hilbert, David Hilbert. So Hilbert was a mathematician, and he asked a series of questions to the mathematical community in that period. So we're straight at the beginning of the 20th century, right? He asked, so he wanted in a way to reach the dream of Leibniz. As I told you, Leibniz wanted a language which was rigorous enough so that you couldn't have any ambiguity in it, and this language would be the perfect reasoning language. So if you wanted to prove something in this language, all you needed to do is to manipulate the symbols of the language using some rule, and you were assured to reach the right answer. Now, Leibniz wasn't able to reach this goal. He tried to formalize such a language. He wasn't able, though. And Hilbert now wanted to actually, okay, let's do it. So let's find a way to have a system, a formal system, which is complete, which is consistent, and which is decidable. So what does it mean? Well, I explained to you what the definition of complete and consistent means. It means that basically the important thing is that using this language, you can always, you will always reach true statements and never false statements. And if a true statement can be composed using the alphabet of this language, surely you can derive it from some axioms. So you define some axioms on your language, and by these axioms, you can reach all true statements, and no false statements. Okay? So you can actually have a discourse with this language about mathematics, and never reach a falsity. Okay? Everything you write in this language, if you follow the right rules, if you actually use the axioms, you're always assured to find the right answer. Now, Gödel answered some of the questions by Hilbert, right? So Gödel was able to prove that you cannot have a consistent and complete formal system, a formal language. You cannot have it because if your system is powerful enough to express some basic statements about mathematics, really about arithmetic, sorry, you reach a paradox. So if your language is powerful enough, it's already written with paradoxes, and that's what Gödel showed. But then there was a last question. So Hilbert also wanted to know, okay, we have this language, we can express all of mathematics with it. Let's say we have this language. So we use our axioms, we reach true statements. But okay, let's say that I give you a statement. Okay? So you have your formal language, I give you the formal system, I give you a statement in this system. For example, a statement could be 1 + 1 = 2. And you have to decide, using effective procedure, if this statement is true or it's false, right? So basically, what Hilbert was asking, he didn't know at the time, in a way, was, well, he did know, but this terminology came out later. He wanted an algorithm, okay? He wanted some program, some piece of software, we would say today, to take a statement in mathematics and say, okay, this is true, okay, this is false. So for example, if I had 1 + 1 = 2, right? You can easily find a way to code out something to check that this is this statement is true or it's false, right? So you do the actual operation with your computer, you do 1 plus 1 equal to 2, you compare with the result of the statement, and you say, yeah, it's okay, it's right, that's the same result I get, so it must be true, right? So Hilbert wanted a way to, he wanted to know, is it possible for every statement to find out if it's true or if it's false? So he really wanted every decision problem, as I explained in the third lecture about the FAs. So a decision problem is a problem which has only 2 possible outcomes, right? Yes or not. So is 1 plus 1 equal to 2? Yes, no. Is this piece of Java code going to run forever? Yes, no. This is a decision problem. So Hilbert wanted to know, is there always a way to decide upon a problem to give a yes or no answer? Is there a yes or no answer to every conceivable, it's not like is there a yes or no answer, but can you find the yes or no answer for any conceivable problem? And that's a pretty good question. I mean, if Hilbert managed to get that language which was completely written, which was completely void of ambiguities, and if it was possible to actually prove every statement true or false using an algorithm, mathematics will completely be solved. Okay, you wouldn't need anything more. So for every possible, so you tell me a question in mathematics. I write it down in symbols using that language, and I run my algorithm, and my algorithm says yes. Okay, this statement is true. So for example, is a circle, I don't know, equal to, so is the diameter of the circles equal to 2 pi? Yes. Oh, fantastic. I have a proof because my algorithm just told me, yes, this is a true statement. Fantastic, okay? So you solve all of mathematics. So Gödel didn't actually answer this question. So maybe my system cannot reach all true statements. So there are true statements that don't derive from the axioms. But okay, maybe I can still find an algorithm that takes a statement in my language and tells me it is true or it is false. He would have probably been happy if you could find such an algorithm. And who answered this question? This question was answered by Turing. Turing proved that actually some problems are you just cannot give a yes or no answer to some decision problems. There are some decision problems which no algorithm can solve. And this has deep implications on our science, because it means that there are some problems. If we face these problems, we can be the smartest programmers. We can have all the time in the world. We can have all the power in the world. We can have a NASA computer, but we're still not able to solve them. There's no way we can solve these problems without a computer. Now, I won't be talking about these problems for this lecture. This is something I reserve for the next lectures, because I just want to make you comfortable with the tool that Turing used to show that some problems really cannot be solved by any algorithm. So that the object invented to show that this was the case is called a Turing machine. And it is a marvelous idea. First, because with that idea, Turing managed to solve this unshading problem, so the decision problem Hilbert posed. But also, this Turing machine, with this Turing machine, Turing was able to formalize the idea of effective procedure. So Hilbert asked for an effective procedure, but he didn't know. He was asking for an algorithm in a way, in the way we think about algorithms today. But Turing say, okay, let's formalize. What do you mean by effective procedure? So if you say effective procedure, I can think about this model, the Turing machine, that can carry out any effective procedure, any algorithm. And because he was able to formalize the very idea of algorithm, he gave us really the theoretical basis for our computers. So he gave us a way to really understand how to carry out computation. So it's not like without these ideas, no computer could be built. Because in fact, computers were built before Turing actually formalized this idea. The first computer by Zeuser, if I'm not mistaken, was built before Turing formalized this idea. But this idea really tells us how computers have to work. So what's an algorithm? How can I program a computer to solve whatever problem I can throw at it, which is solvable? And he did that by showing that a Turing machine, so there's a special Turing machine, which is called a universal Turing machine, which can run any algorithm, which can run other machines. So it's a machine which can run other machines, okay? Think about it, well, to give you an example. Well, this is exactly what your CPU is doing in your computer, right? It is reading in your hard drive some program, and it runs that program. So there's a program inside your CPU telling your CPU how to read out other programs and carry out their operations. And I will show you how this is theoretically possible. So how a universal Turing machine works, and by understanding how a universal Turing machine works, you will have a deep understanding of what's happening at the lowest level in your CPU. So what's your computer really doing? Because of course, we tend to think about computers at a very high level, right? So we're used to code in high-level languages, okay? Even assemblies, it's not the deepest level you reach in programming, right? The Turing machine actually is. So we don't see all this complexity, and this leads us as computer scientists sometimes to forget what our computer is really doing, what's the real nature of what we're doing, right? Which really is just symbol rewriting and pattern matching. So in the end, when you look at the deepest nature of what we do, when you reach really the deepest level of what we do, this is nothing different from pattern matching and symbol rewriting. It's just that you do it in different ways. You have different models to carry this out. You can think about many different Turing machines which rewrite, pattern match different things, but in the end, the operations you carry out in your computer is always pattern matching and symbol rewriting. You cannot escape that. And all our computers are just doing that in the deepest level, right? So when people tell me about consciousness in a machine, consciousness in a digital computer, I'm really skeptical, because in the back of my mind I have the fact that really computers carry out just two operations. There are actually three. We will talk about this later, but in the end it's just really pattern matching and symbol rewriting. And I find it difficult to reduce all of a human mind to pattern matching and symbol rewriting. One student asked me this question: so do you think it's possible to have super Turing computations, or to go beyond this pattern matching, symbol rewriting? And my belief is yes, we can go beyond, because I think that human beings perform super Turing computation. The problem is, it's really difficult to show that, because all the computation we know is digital computation. We don't have any frameworks to work with any other computation. And actually, there's a thesis, the Turing thesis, which says basically all computation is somehow Turing computation. So all effective procedures are Turing machines, and all possible models of computation, of reasonable computation, so of computation you can really carry out with computers are somehow mappable to a Turing machine. Okay? So all possible models of computation are really the same thing. And this is how we think about computation in this moment. I don't know if we will ever find out anything else. It's possible that actually the whole universe is digital, so we live in a digital universe, and the whole universe is just a Turing machine. Somehow deep in the deepest layer is just Turing machines. That's possible, but we don't know. And I'm open to the alternative that we're more intelligent than Turing machines. And now I'm going to explain to you what Turing machines are, and you see that really they're stupid machines, meaning that all the intelligence which you pour into the programming of these machines comes from you, not the machine itself. So, okay. So we talked about DFAs, and we saw that they can solve some problems. But a DFA is composed by a finite number of states, and the only way they can really encode memory, which they can have memory, is by using states. So if I have, each state is somehow saying, okay, I come after these other states, so I know more or less what happens before. But because every DFA has a finite number of states, that means that the amount of information they can encode, or the amount of things they can remember, is finite. There are some problems, though, that require unbounded amount of memory to be solved for every n. For example, the problem of balanced parentheses. Every time in your program you open a parenthesis, you must close it. Now, because DFAs have a finite number of states, you can ideate a DFA which can match 1,000, a trillion billions parentheses, but not 1,001, a trillion billion one. Okay? So we needed another model. What we did is just, okay, let's add a stack to our DFA. Let's give our DFA the possibility to write at the top of the stack, and to pop it, and to push, and to read it. And by doing that, we get an unbounded amount of memory, and we can solve many more problems. We discovered that actually, yeah, you solve many more problems than DFAs, but there are still some problems you cannot solve with PDAs. And the reason why you cannot solve them is that, yes, your memory is unbounded, but you cannot access whatever point in your memory you want. But your only access to your memory is the top of the stack. Okay? So we discovered that actually not all problems can be solved by PDAs for this reason. So we need more. What we need is to give our machines a random access memory. Okay. So a machine that can read its input, has an input tape, can read its input, and somehow has a memory, and this memory is unbounded, like PDAs, because we know what happens if we have bounded memory. And this machine can go anywhere in its memory to read anywhere it needs. Okay? Actually, you can collapse input tape and memory. So your machine can just use the input tape, because it's infinite. It can use the input tape as a memory. Okay? So your Turing machine in the end will look something like this. You have a tape. You have a read and write head. Okay. You, like in DFAs and PDAs, you have a state control. State control. So you can have different states. And the thing that your Turing machine can do is move freely on this input tape. So let's say that your input is 0, 1, and what your machine is doing is just reverting. If you find a 0, make it a 1. If you find a 1, make it a 0. What will happen here is that you start in an initial state, you find a 0, that the machine rewrites it in a 1, and then it moves in another section of the memory and does the same, put it like in a 0. Okay? So that these are the actions that a Turing machine can do. It can move on the input tape and rewrite the symbols. Okay. Some differences with PDAs. First, a Turing machine is not tied to the input, meaning that if you remember, well, let's say if we have a PDA, right? Sorry, a DFA. Let's make it simple. You have states. I don't know, A and B. Okay. You have an initial state, and you have an accept state. Okay. But let's say in this case, for example, you have this machine is accepting all strings that begin in A and in whatever number of B's. Okay. So let's say that you have A, this is accepted, but then you get another input which is B, and you're still in accept. You get another B, you're still in accept. So in a way, the computation can run. You can still run while you're in the accept state. Okay. Turing machines are not like that. Turing machines are really strict in this way. So once the Turing machine decides to accept, so to halt the computation to accept, it actually stops. So in this case, for example, let's say that the input continues. The Turing machine can simply decide to not continue. So you don't have to read all of your input tape. You don't have to substitute more symbols that you need. You don't have to do anything with the Turing machine. At a certain point, you can just decide to stop. And this is actually, if you think about it, is quite straightforward, meaning that if you think that a Turing machine is just a way to formalize an algorithm, you can devise an algorithm that stops whatever it wants. Okay? So for example, yeah, you don't have to have an algorithm which loops until the input is finished. You can say, okay, read just the first 3 symbols and stop. Okay? And the same for the reject state. In Turing machines, you have a definite reject state. It's only one. So you have an accept state, a reject state. And if you reach the reject state, you reject. There's no way back. So you're just saying this string is rejected. Whatever input is left, I don't care. I have rejected. So once you reach the reject state, you don't move anymore. So to make it more... Okay, I first want to build better your intuition of a Turing machine. So I'm going to show you an example, and then I'll make it more formal, this definition I gave. So this example I programmed on this nice website. I programmed a Turing machine which decides if you have strings which are composed by the same number of zeros followed by the same number of ones. So in this case, our string will be accepted. So now I'm going to run the Turing machine just to give you an idea of what's happening. So here you have the state of the Turing machine. You can see that it changes while the computation goes on. You have the input tape, which is unbounded, left and right unbounded. You have symbols, and you have a read and write head, which can move on the tape. Okay? So let's see how this Turing machine solves the problem of establishing if this string is in the language. So if this string is actually formed by an equal number of zeros followed by an equal number of ones. And make it slower because here it is a little bit too far. So you see it moves and it uses symbol to mark. Can you actually see? I think so. So let's see it again. I make it a little bit slower. So the head moves on the tape and it rewrites some symbols. And in this case, what it is doing is just marking for each 0 you mark a 1. So if in the end you get an input which is all marked, it means that you have to accept you have the same number of 0s and 1s. So in this case, you stop the computation and you accept. Okay, let's try out a symbol, a string which it should be not accepted. So in this case, it should be not accepted. You have more 0s than 1s, right? So the Turing machine moves on the tape. It rewrites whatever symbol it needs to rewrite, and in the end, it finds out something is wrong. There should be 1 here. So the Turing machine goes to a reject state, and the word is rejected. A third example, just to show you that you don't need to consume all the input to reject or accept. Oops. So the Turing machine mark a 0. Now something wrong is happening. Okay. Well, in this case, all the input was consumed, and I should change the code to make sure I showed you that you need to consume all the input. But anyway, I won't show you that, and you're smart enough to understand that the machine could have just stopped here without reading any 0s at all, and that means that some symbols wouldn't even be read, not even once. So the Turing machine it's completely untied from the input, so it moves on the input, does whatever it wants. It's not tied to the input like DFAs and PDAs are. Okay. So, to put it more formally, the important thing about Turing machine, so I won't give you the complete formal definition, but something you need to know is that you have a delta function, exactly like PDAs, exactly like DFAs, so a transition function, which maps from a state in Q. Q is the set of states, and some symbol in the tape, gamma, it maps some other state, some other symbol, so it rewrites a symbol, and then it moves left or right. Okay? So this means, is it horrible? It's a little horrible, I guess. But I guess you can read it. So what this means that at every step of the computation, the Turing machine does two things. It is in a state, and it reads something from the input tape. And based on the state and the input tape, and the symbol on the input tape, it goes to another state, it rewrites that symbol with something else, and then it moves the red and right head either to the left or to the right. Okay? So the way you specify a Turing machine is to give instructions of this type here. So for example, in the case of the Turing machine simulator I used here, what I do is exactly that. I specify a certain number of transitions, saying, for example, okay, if you're in state back to X, I just gave names so that I could remember what they did. So in a state, you're in a state back to X, you read an X, you go to state mark 0, you leave the X alone, and this means you rewrite an X, but because it's the same symbol, it's just saying leave the X alone, and then move right. Or if you are in mark 1, in state mark 1, and you read a 1, you move to another state, back to 0, you rewrite that 1 with a Y, and then you move left. So, as you can see here, we're actually moving towards the concepts we know in programming, right? So, if you ever programmed in really, really low-level languages, it looks something like that, right? So you have really to specify, teach computation step really what to do, okay? We're getting closer to the level we normally work in. So, okay, I told you what the actions of the Turing machine are. Now I'm going to, first, are there any questions? I always forget to ask you, so if there are any questions, just shoot. So, yes, I want to introduce you to as a way of annotation, okay? I want to introduce you to a shorthand. So, if we were to actually take snapshots of every computation step of a Turing machine, what would we have? We would have something like that. So we have a tape. Let's say our input is 0, 1, 0, and you have the read and write head in some symbol, and you're in a certain state QI. So this is a configuration of your Turing machine. Okay. Let's say that in the next time step, let's say that you have your transition function is saying, okay, if you're in QI and you read a 0, rewrite 1 and move to the right, and change state to QK. So what if we take a snapshot? So we're rewriting 0 to 1. We're moving to the right. And we're changing the state to QK. Okay? So we can do that for every step of the computation. We can draw this little diagram, and this gives us all the information we need to interpret what the Turing machine is doing. Now, there is a better way to write this down, meaning a shorter, more elegant way, which still gives us the exact same information, which will be something like that. So if I wanted to rewrite this in the form I want to introduce you to, we would have this would be equal to QI 0, 1, 0. And this will be 1, QK, 1, 0. So this notation here, I see some of you are nodding, it is quite simple. So what you're doing is, you write your state at the left of the symbol where you have your read and write head. So your read and write head is in 0. You write the state, QI, at the left of that symbol. Okay? Same here. You read and write head is on symbol 1, and the state is QK. So you put QK at the left of 1. And this is giving you exactly the same information, but you don't need to write, you don't need to draw the read and write head, the state, the tape. You just need to write down a concatenation of symbols. So, yeah, I think that's so. And if we know that given this input and this position of the read and write head and this state, our next state will be, our next configuration will be this one. We say that this yields this. So QI010 yields 1 QK 1 0. Okay? Quite easy. I could make it more abstract, just to make sure. Yeah, I'll just make it more abstract. So you have some symbol A, B, C belonging to the set of symbols, and some strings U, V belonging to the clean star of the set of symbols, because they're strings. And you have some states Qi, Qk. Okay. I want to first explain to you why this gamma here. So normally when we talk about alphabets, we use a sigma. It's just the way we do it. So in this case, we use gamma because actually the alphabet here is called a tape alphabet, which is not only the input alphabet, but also the symbols I need in my Turing machines to work, right? So for example, in the Turing machine I showed you on the website, the input alphabet will be 0 and 1, okay? So you have strings of zeros and ones. But then the Turing machine uses also X and Y to mark them. So they're still part of an alphabet. And the total alphabet is called gamma. It's the alphabet, the tape alphabet, the tape alphabet. So the union of the input alphabet with the symbols that the Turing machine needs to perform whatever computation it is computing. So we have this, and let's say that we know that delta Qi and B gives you Qk, C move to the right. So I give you two transition functions which do exactly the same thing, but one moves the tape to the head to the left and one moves the head to the right. Okay? So in this case, if our configuration was something like this, U, A, Qi, B, C, and we had this transition here, what will be the next configuration? What will this yield? So we're following this delta here. So we have a rule which says, if you are in state Qi, we are in state Qi, and we're reading a B, we're reading a B because the state Qi is at the left of the B. This is our rotation. We go to state Qk. We make a B a C, so we rewrite B with C, and we move to the what's the first one? We move to the right. So what should I write here? What would be the correct yield?
Say UAC QK.
C. Exactly. Very good. So here you would have Q, A, C, QK, C. Oh, actually, let's put a V here and a V here. So this this U and V are just some strings. So just to say, okay, there is something on the left of the right head, there is something on the right, some strings, some other symbols, it doesn't matter. And then I have a symbol, another symbol, and then what I do is, as you say, I rewrite this B and then move to the right. So this B is now a C, and I move to the right, and QK is our new state. Okay, so this is the yielding. If I were to follow the second one, so if I were to follow the second transition, what will be my yielding for that? So we're here, right? I'm in state Qi, sorry. I read a B. I change my state to Qk. I write a C. I move to the left. What will be the next yielding for this configuration here?
QI A C C B.
I move to the left. Yes, you're right. A U Q I A C C V. Why is that? Because okay, we're saying if you read B and if you reset the I and you read B, you rewrite this B with a C, and you change to state QK and you move to the left. And this is exactly what's happening. You were there, you rewrote that B in a C, and you moved left. So be familiar with this notation because I will ask you to use it. Okay. So now I gave you all the definitions you needed. I will say let's do 10 minutes of break, and in the next hour we will start actually doing some examples. So I will build some Turing machines to solve some problems. I will show you the simulation, all of that, and so you can understand really how they work, okay? So 10 minutes of break. Okay, okay, let's start the second part of our lecture. So for the second part, all I'm going to do is just doing some examples of Turing machines, so you get a feeling of how they work, really, and you get accustomed with the diagram notation, which is really similar to the one from the FAs and the PDAs. It's really easy, actually. And you can actually, with this example, you should start to feel why every algorithm you can think of can be mapped back to a Turing machine. Hopefully, you will start to understand that. So, let's say we have this language here. 0n, 1n. And we want a Turing machine which can accept all strings of this form and reject strings which are not on this form. So what would be an example of strings of this form? Well, 0, 1, well, even the empty string is on this form. 0, 1, 0, 0, 1, 1. So you have a number of zeros and you have the same number of ones, okay? So if I gave you the task to find an algorithm to solve this problem, how would you go about it? I'm sure you're able to solve this problem because you're already second year of computer science, so I'm sure you can write some code to solve this problem in 1 minute top. So the way I will be solving this problem is, I don't know if it's the smartest one, but it's our way, and 0, 1, 1, 1, it's a little bigger. So the way I want to solve it, which is very easily implemented in a Turing machine, so I don't have to spend 1 hour devising a Turing machine to solve it, I can spend 5 minutes to devise it. The strategy will be the one I showed you in the previous example on the website. So I start, my red right head, let's say, is here. So I start reading, actually, as a human being. I start reading, and I say, okay, I have 1, 0. I mark it with my pen. I have 1, 0. Then I go to the ones. So the first one I meet, I mark it. I go back to the zeros. The first 0 I meet, I mark it. The last 0 I meet, I mark it. Or you can think about this as saying, I mark the 1, I go back to the first marked 0, I go to the right and I mark the 0. So I do this, I go to the first marked, so I go to the marked 1, I check that there's a 1 which is not marked on its right, and I mark it, I go back, mark a 0, I go forward and I mark a 1, and then I check if there's nothing else. If there's nothing else, I solve this problem. So this will be the algorithm. Start marking zeros and ones until everything is marked. Okay? So it's a really easy way to go about it. And Actually, I want to tell you this. When Turing invented this Turing machine, when he devised this object, this mathematical object, what he had in mind was actually a human being with an infinite amount of paper, a pencil. Well, actually, the paper was squared papers. Square paper. Huh?
Rough paper?
Rough paper? Well, the one with the squares, the one you use in mathematics, right? So you write a symbol in each block, in each square, and you can write symbols with your pen. And the idea was to have a really stupid, let's say, human being, which would only follow the instruction. So the only thing he could do would be, well, on the form I showed you. So if you're reading now this symbol, read the symbol on the right, maybe do a mark, maybe read the symbol on the left. But this was what he had in mind. So an actual human computer, because up to this point, up to the point of Turing, there was no computer as we think about, right? So computers were actual human beings carrying out computation. So now, after this digression, so we solve the problem this way. We just mark ones, zeros and ones, right? So to put it in the form of a Turing machine, let's do a diagram. We love diagrams in this course here. So we start in some state. The first state will be, so the first instruction, let's say, that I want to carry out is mark a 0. So the first thing I need to do, if I have a string of this form here, the first thing I need to do is to mark a 0, right? So I'm here, I mark my 0. So let's call this state mark 0, right? So, well, first of all, to mark a 0, I need to read a 0. So, if I read a 0, I put an X or mark. In my case, the mark I want is an X, let's say. Okay? I put an X where the 0 is, and I move to another state. And I move the read-write head on the right. So I try to see if there's another 0, for example, or anything else, okay? 0, put an X, and move to the right. So this is the notation, okay? Well, let's put a state here so you can see the whole picture. Okay. So this is the diagram, how you write down the diagram. So you have a state, you have a transition, and for each transition you specify what symbol you want to read to take that transition, with what symbol you want to substitute it, and where do you want to move, to the right or to the left of the tape, okay? So in this case, we're at 0. We read a 0 here. We read a 0, and we substitute it we rewrite it with an X. But this is our tape. Oops. It becomes an X. And then we move to the right. So let's see what's after this 0 here. So what we want to do now is skip all the zeros and try and find a 1 to mark. Okay, this is the next step of the algorithm, right? So we mark the 0. Let's find the correspondent 1. So how did I call it here? Okay. So okay. Let's put a transition here saying if you read a 0, leave it alone, or you can think about it, rewrite it with the 0, it's the same, and still move to the right. So this says you take this transition for each 0 you read, and you always move to the right. So in this case, I will read 0, move to the right, 0, move to the right, and then I read the 1, and let's see what happens. So what I want to do now is to mark this 1. So if I read a 1, I want to mark it with another symbol. I choose Y and move to the left. Let's go back. So I will call this state here mark 1, because what I want to do in this state is find the 1 to mark, right? So again, I start with the 0, I mark it. I skip all the other zeros, I find the 1, I mark it. And then I want to go back to x. What I want to do now is, so let's say that I marked the first 0 and I marked the first 1, y here. I am now here, my read right here, my read right heads here. What I want to do is find the last x and go to its right to mark again, to restart the cycle, and mark a 0, and then go and mark a 1. Okay? So what I want to do is skip, so jump again all zeros. So every time you find a 0, you go to the left. If you find a y, you go go to the left. So you do both. So this is for the second cycle. So I write it down later. So let's call this go back to x. And again, if I find an x, I restart the cycle. So I have this loop here. If I read an x, I leave it alone, and I move to its right to see if I can mark another 0, right? So let's follow this loop. So let's do it. I read a 0, I mark it with an x, right? Then I'm now in mark 1. I'm in mark 1. I skip all the zeros until I find a 1. I mark it with a y, and I go to this state here. So my read write head is now here. I mark it with a y, and I go back to x. So for every 0 I read now, actually I marked it with a y, but I am now here because the movement here was left, right? So I reached the 1. I made it a y, and I went left, which is left. So now I skip all the zeros, I go left. Every 0 I see, I just go left, 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 until I find an x, and then I go to the right of the x, and I restart the loop. So what I do is, I'm here, no, I'm here, no, I'm here. I read an x, and I go to its right. I'm now here in mark 0. So again, I mark it with an x, and I go to the 1, and I mark it with a y. I go left. Now we need another transition here to go back to 0, because now we're reading a y, right? But we don't have a transition to say skip the y. So we add it. I added it before. Y, leave it alone, go left. This transition, I go left. I read a 0, I go left. I find an x. Again, I'm here. I go to the right of the x. I mark the 0 with an x. And then again, I go and find a 1. Found it. I put a y. And then, again, I go back. And I don't find any 0, right? So I go back, I mark 0, but I don't find any 0. There's no 0 anymore. So once I reach the x, if I go to the right of the x, I find a y. I don't find a 0 anymore. So I'm now here. What to do? Well, here I want to accept, right? Because it means we marked all the numbers. It seems that there are no zeros left. So let's add a state which say something like all zeros marked. I get there if I find a y here, a y, leave it alone, and move to the left one. Actually, no. No, let's move to the right, because now that I know that all zeros are marked, so there are only x, I want to make sure that all ones are marked, right? So what I want to do is move to the end of the input until I find a blank symbol. So in Turing machines, we actually have blank symbols, meaning that in that square, let's say, in that portion of the tape, there's nothing. It's like it's not the empty string, it's an actual blank symbol. James, if you remember, you asked me about the empty string last time, right? In this case, the blank symbol is actually part of the alphabet of the Turing machine. Okay, so this blank symbol is actually part of the alphabet. It's different from the empty string, which is just a way of notation. Okay. So what I want to do now is I am in y. I go and find if I can actually find a blank symbol before I find a 1. So if I find a 1, I have to reject it. It means that there are more ones than zeros. But if I find a blank symbol, it means perfect. I can accept. So what I do here is just loop. Every time you find a y, leave it alone and move to the right. And if you find a blank symbol, just accept. Okay? Now, if you remember, oops. One notice. Okay, I'll leave it there. So, if you remember, I told you that there are distinct accept and reject states in a Turing machine, and there's just one of those for each. So you have one reject state, one accept state. In this case, you don't see any reject state, but actually it is there. I just don't draw it because it will make the diagram very messy, but it will be something like that. Reject, right? And for every, let's say, for every transition which is not present in this diagram, it goes to reject. So for example, if I'm in mark 0, I have a transition for 0, okay, I know what to do. I have a transition for y, okay, I know what to do if I find a y. But there's no transition for x. In that case, I would just, if I read an x, something went really wrong in my computation. This is something unexpected, I reject. So every transition which is not in this diagram, you have to think about it like going to reject, okay? And you stay there forever. So once you reach an accept or a reject state, there's no way back. It's the curse of Turing machines. So, let's see it maybe another time here. Just to make, well, I did already show you, but okay, just another time for old time's sake. So let's see what we're doing here. It's just moving on the tape and rewriting symbols. And at a certain point, if we are happy with what we see on the tape, let's say, we just accept. In this case, you see, I move here, I see a blank symbol, no ones anymore, and the word is accepted. So here for the first example. Okay, now you know more or less like how a Turing machine works. You know how to draw and how to read transition diagram. Now, what I want to show you is that you can actually use Turing machines as subroutines. Okay, Turing machines are like functions you can call in a way, meaning that you can have a Turing machine actually calling another Turing machine to do some computation. Okay. So for example, let's go to one note. So let's say that I have this language here. Okay? So you have the same number of zeros as ones as zeros. So you have some number of zeros, you have the same number of ones, and then the same number of zeros. Again, if I asked you to solve this problem, you could code something very easily, okay? You could, the way I think instinctively, the way I would solve it would be to just program some counter, okay? And just count the zeros, and then count the ones, and then count the zeros. That's the most straightforward way to do it. Of course, it can be done on Turing machines, because as I told you, they're completely, so everything you can do in your code, you can do it in a Turing machine. But you have to reserve a part of the tape to do to work as a counter, and it's slightly more time-consuming, not difficult, really time-consuming than do it in another way. So the way I want to do it is, because we already solved the problem of recognizing 0 to the n, 1 to the n, we already have a Turing machine for that. Well, let's use it. Instead of rewriting everything, let's just the way I want to do it is actually a little different from how Seraphim does it in his notes, which I put it online. So he solves the same problems, but I solved this one in a little different way to better illustrate the point. Okay. So the way I want to solve it is, we have a machine that recognizes that. So I have a machine that can tell me, okay, yes, we have the same number of zeros as ones. Then what I want to do is go to the second part of the string, reverse it. So instead of ones and zeros, every time I see a 1, I make it a 0, and every time I see a 0, I make it a 1. To have this. And then do it again. So let's reuse, I want to reuse the 0 and 1 and Turing machine again. I want to call it 2 times. Okay? So let's do it. So, now the problem we have here is that, of course, we don't want this machine to accept. But what we want to do is, instead of going to the right of the last one and try to find a blank symbol to accept, if you find a 0, carry on with the computation. So that's what we want this modified machine to do, okay? So if you find a 0 in the end, so here you would have that, what was the name of the state? You would have this one. All zeros marked, but instead of blank, blank, right, I want to put 0, 0, right. Okay? So that's what I'm going to do. Left, right. So this will be all ones marked. Fine. So once I do that, it means that I'm reading the first 0. So let's actually write down a string of this form so it's easier to understand what's happening. So once I recognized all these strings here, what I end up with is something of this form. X, 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 Y, 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 because I marked them, right? So what I want to do is, okay, I read 0, I leave it alone, and actually I want to go to the left and write some symbol. Oh, no, actually, I want to move here to the first X. Yes. and write some symbol which says, okay, don't go, so don't actually read what's here, it's garbage, just focus on this string here, and make these zeros and these ones, so that we can reuse again in our nice machine. Okay. So it's quite straightforward to do it with a Turing machine. Here, I did put the right symbol. So I call this state read init, like reinitialization. Read init. I'm here in this moment. I just solved the first part of the problem. I just moved to the left. I found a y. What I want to do is, if you find a y, just go back and until you reach an x, right? So, find a y, leave it alone, move to the left. And if you find an x, substitute with a symbol which tells me don't go further than here, and then move to the right. So, I was here, I moved to here, and I substitute the symbol with that dollar sign. Just to say, on this side is all garbage, don't go there. Okay, so now here. And I move to the right, and what I want to do is, what I want to do now is, well, it's easier. It's easier if I just go to the end of the string until I find a blank symbol, and then I start reverting these back. These ones become ones, and these ones become zeros. So go to end, meaning whatever you find, just go right. So y, go right, 0, 0, go right. But if you find a blank symbol, you leave it blank and you go left and you start reverting, meaning that if you find a 0, make it a 1 and go left. If you find a y, make it a 0, go left. And if you reach the dollar sign, meaning you reach the end, just leave it alone, move right, and start another 0 and 1 and machine. So I now want to, and of course, this is actually the actual machine. We don't need to do any modification, right? If it accepts, accept. If it rejects, reject. So this example was to show you that you can reuse old Turing machines as subroutines, exactly like you will do with an algorithm, right? Sometimes you can think about an algorithm and you can divide it in your mind in sub-problems you need to solve. That's no different from what Turing machines do. I want to actually show you how this example is carried out by Turing machine. So, is it this one? No, this one. So let's go to the website. I had to say thank you to this guy here, because for a minute I had the thought, okay, maybe I should code my own Turing machine simulator, but then I found his, and that saved me quite a lot of time. So compile, and let's put input. Not sure I loaded the right one. Let's load it. So you start with the normal 0 and 1 end machine, right? So you start marking, you start, and you solve the first problem. So now you try and go to the end, see if it's a 0, there's a 0. You go, you put the dollar sign, and then you go to the end and start reverting the string back. As you can see here, what I did is I just made the tape a problem I already know how to solve, right? So again, here I have 0n, 1n. I know how to solve this. I run exactly the machine I invented before, right? So I do exactly the same, start marking. Let's wait until it accepts. Hopefully I didn't do any code mistakes. And it accepts. Okay? So again, now you see how really Turing machines get nearer and nearer our world as programmers, other than computer scientists. So this is So, okay, now I will actually show you first the example and then try to do what? Yes. And then devise, so. Okay, so these problems, the problems we have solved up until now, are context free. So something like that I can solve with a PDA very easily, right? You can think about a context-free grammar which generates these strings. That means that you can find a PDA that solves this problem. Okay, so if you already, if you can see a string and you say, I have to recognize these strings. What model do I use? Well, if you, in this case, for example, if you find a grammar which can generate this string, that means you can find a PDA, right? So this equivalence is nice in terms of problem solving for us. So let's have a problem which is not context free. So the language I want to recognize now with our Turing machine, which recognizes context-sensitive languages. So we went up another degree in the hierarchy. So let's have a context-sensitive language. An example will be this one. Okay. So you have a number of n, and then you have a squared number of ones. So if I have 2 n's, I expect to have 4 ones. If I have 3 n's, zeros, so if I have 2 zeros, 4 ones. If I have 3 zeros, 9 ones. It's 3 squared. If I have 4 zeros, 4 by 4, 16 ones. So it's the square, right? Turns out I need more power than PDAs to solve this problem. You already see that square there looks really. How do I solve this with a PDA? How do I use a grammar, context-free grammar to generate this? So one way, this is huge. So the way I want to solve this problem here is to, okay, I'll show you a string in this language, and then so 0, 0, 1, 1, 1, 1. So a way to solve this is have a nested for loop. Okay, so that means I take a 0 and I make sure the way I want to solve this. For each 0, I copy the whole thing here to the right. I have a 0, 0. Then I have the second 0. Again, I copied this to the right. 0, 0, right? And then I end up with a problem I know I can solve. Okay? I make an example with 3 zeros then. 0, 1, 1, 1, 1, 1, 1, 1, 1, 1. So what I want to do is have the same number, so I have n squared number of zeros to this side, and then just start marking exactly like I did before. Okay? How to do this? Well, n squared zeros are a way to do it. So the way I chose, you could find another way, another Turing machine, but the algorithm I chose will be to, for each 0, copy the whole thing to the other side, right? So there's 1 0, you do 0, 0, 0. There's another 0, you do 0, 0, 0. So you see there's a nested for loop. It's like you're looping 2 times. You choose a 0, and then you loop 0, 0, 0. You choose the second 0, you loop 0, 0, 0. You choose the third 0, you loop 0, 0, 0. And you get exactly n squared zeros. Okay? So once I have that, I can use exactly the same algorithm as before. So before I had this machine here, so I had a machine which could recognize this. Now we have the opposite, we have 1n, 0n. But of course, it's exactly the same machine, I just invert the symbols. So what I do here is, so I do this double for loop here, and then I start marking 0, 0, 1, 1, 1, 1. And then I accept. So I discover that effectively I have n squared ones, because I created n squared zeros, and I was able to mark all of them. So this is probably not the most efficient way to do it, but it is a way, and it's not too hard to write it down in the form of a Turing machine. So I won't probably have the time to finish this, but I start anyway. So I want 2 machines. The first one copies n squared zeros to the right of the ones. And then I have the usual machine I know that marks 1 zeros, 1 1. Okay? So let's build the first machine. How to call it? Let's call it 0n. You have some ones here, so let's put it like regular special form, and you copy these to the right. So we call this the machine that copies n squared zeros to the right of the ones. I don't have any better name for it. So how to go about this? Well, okay, let's have a string. What we want to do is have this loop 3 times. 1, 2, 3, 1, 2, 3, something like that. Okay, how do we go about it? Well, what we need to do is to mark, so have 2 kind of marks. One mark which is telling me I already saw this 0, so I already copied this 0 on the other side. So this will be like an inner loop, and then the outer loop which loops through every 0. So you're here. Okay, I have 2 marks. I have 2 ends, I have 2 marks. So you're here, you mark this, you copy that, mark this, you copy, you mark this, you copy, and you have the first chunk. Okay, so you mark the first 0 to say, I already copied this, so I did the first chunk. And then you superimpose, let's say, again, mark the first copy, mark the second copy, mark the third copy. Okay, I copied the second chunk. Let's mark this one. Okay. Actually, I will show you the example. So you see. Oh, I have to copy the code first. So let's go. So let's have, 3 zeros is okay. I'll put a 1, because this machine needs a 1 to say copy to the right of the 1. Okay. So what happens here is, let's start. I'll make it slower so I can talk. So you copy the first 0 and you mark it, right? So Z here is marking, I copied this 0 to the other side. Okay, paste, go back, mark 0, and go paste. Okay. Now we need another mark to say the first 0 is gone. So I did the first chunk. I need to move to the second chunk, to the second chunk. So let's go. Let's go back, reinitiate 0, 0, 0, and mark the first 0 with an X. So I already saw it, and let's do the second iteration of the loop. So let's go back. Okay, here I need again to mark it, right? So I need to copy all of these 3 to the other side. Problem is I cannot use a Z here, right? Because if I do so, I lose the information that I already saw. I already did the first chunk. So if I rewrite this X with a Z, my machine doesn't know anymore that the first chunk was done. So I need actually a third mark, which is a mark which is saying that both marks are present at the same time. So I would put a Y to say that the chunk was done, and that the 0 is marked. Okay. So I make it a Y, and then again Z. Oh, what's happening? Of course you have to copy the first 0. So you copy the first, then you copy the second, Z. I can actually speed up this, and and you copy the third. Let's make it a little faster, come on. You see? So we are at the second iteration. There's 2 X's there. There's 2 chunks I already did. And now, again, I go back, and this will become a Y, meaning that there's an X and there should be a Z as well, but I use a Y because I cannot do that. So Y, Y, Z, and I copy all of that again. Let's do it. Y, Y, oh yeah. I copy the first 0. I copy second 0. And I copy the third one. And that's good. Again, I put an X. And I'm done. So this machine here copied exactly n squared zeros to the right of the 1. So I know this machine exists. Now I should write down the transition. Well, I'm not sure that's a good idea. Let's see where I get from. Okay. So what will happen is that I will start writing down the transitions, but we will have to finish it in the next lecture. So, again, let's build this zero, so copy n squared zeros to the right of the 1 machine. So, let's use an example. So what I want to do is, I start from 0, so what I do is mark 0 with a z, which means basically copy that 0, right? So mark 0 with a z, so that 0 becomes z, and I move to the right. I'm now here. This is now z. What I want to do now is skip all the zeros, skip all the ones, go to the white space, to the blank symbol, and make it a 0. So I'm pasting what I copied. So mark 0 with a z, go to end, let's say, go to end. Is that a good idea? Yeah, okay, let's do it that way. Jump zeros first. Jump all zeros, so that if you meet a 0, you leave it alone, you move to the right. Then, if you find a 1, leave it alone, move to the right, and jump all, if you have other ones, you do the same, right? So we call this jump ones. And then, actually really here, if we jumped all the ones, we can paste 0. So if we meet a blank symbol, we make it at 0. We paste, and we move back. Okay? So we're here, and we jump back jump, let's say we jump once, so that if you meet a 1, you stay 1, you go left, and well, these are already what I will do. So this, okay, I don't want to go forward because otherwise I'll start and we just get, we stop in the middle. So what I stop here and I say, this is the first cycle, right? So this is the cycle where I go to the first 0, I mark it as a z, I go to the end, I paste a 0, and I start to go again back until I find a z, I move to its right, I didn't write this, and I make it a z. So this will be the next steps. I would say let's stop here so that on the next time we can move from here and complete the problem, okay? So on the next lecture, I will complete this example and I'll be talking about context-sensitive grammars. So I talked about Turing machines. Now we will see the grammar point of view. It will be a simple lecture because I won't go in depth about it. But after that, we actually move to the universal Turing machine, and that's where things get interesting.